Today we're having Hudson LaFayette talk about coloring P5 gem free graphs with delta -1 colors. Take it away.
Yeah, thank you so much. This is joint work with my advisor, Dan Cranston, and also Landon Rayburn. So to set up, all graphs for this talk will be simple and connected, as God intended. And the chromatic number, maximum degree, and clique number will be chi, delta, and omega, respectively. So we'll start off, of course, with Brooks' theorem. That's whenever you're talking about coloring, Brooks' theorem is, or vertex coloring, it's always there. You might not have seen it phrased this way, but delta at least 3 blocks the fact you're an odd cycle. Your clique number at most delta blocks the fact that you're a clique. So this is Brooks' theorem. If you're not an odd cycle or a clique, you can color with delta colors. It's phrased this way so you can clearly see the conjecture by Born and Kostochka is a strengthening of Brooks' theorem with very similar hypotheses. And so you can color with 1 fewer colors. Another sort of related conjecture is Reed's conjecture. Its chromatic number is bounded above by the ceiling of delta plus 1 plus omega all divided by 2. And the Born and Kostochka conjecture is stronger only when the clique number is delta -1 or delta -2. Otherwise, they're equivalent or Reed's conjecture is stronger. And so this talk, we got a paper that proved Reed's conjecture for P5 gem-free graphs. And they had a structure theorem, and we used it to prove it for the Born and Kostochka conjecture. So it's just a sort of slight improvement in certain scenarios. Again, here's the conjecture, so you don't have to memorize it. Whenever you see a conjecture, you want to know if there's free real estate. So, can I tweak some small little thing and get a cool result from it? But this conjecture was well stated from the start. Just to show you, if you weaken the first hypothesis, the conjecture becomes false. Here's a counterexample. Delta equals 8. Clique number is at most 8 - 1, but you still need 8 colors to color it. This right here is what's called a clique expansion of C5. So you get each vertex, you blow it up to a clique, and if there's an edge in the original odd cycle, you put a complete bipartite graph between the corresponding cliques. So these thick black bars for this talk are going to be complete bipartite graphs. So if you see those in an image, that means all edges are present. The second hypothesis, if you try to strengthen it, the result is not strengthened. Here's a counterexample, delta equals T. Your clique number is delta -2, but you still need delta -1 colors. And so this is an odd cycle on 5 vertices with a complete bipartite graph between a complete graph on T -4 vertices. So this conjecture is well stated. There's nothing for free that you can get here, so you just got to prove it straight up. So here's some known results on it. Here it's stated in the contrapositive. And again, to get you like a layman's perspective of this conjecture, this statement I'm about to say is not true in general, but it's sort of intuitively true. A false fact, I guess, is the clique number being at most delta -1 means you're not anywhere locally dense. So you should be able to color with relatively few colors. And so the contrapositive is saying if you need a lot of colors, then somewhere you should be locally dense. So that's one way to sort of have this conjecture stick in your head. And some known results to point to this being true is it's true for claw-free graphs. Cranston and Rayburn proved in 2013. The dash-free meaning we're forbidding it as an induced subgraph, so claws can't be induced. We'll see that dash-free later in the talk as well. Reed in 99 proved an awesome result where delta sufficiently large suffices. The conjecture is true. 10 to the 14, he used probabilistic method. You could bring that down, he said in the paper, to 10 to the 3 if you were really careful with the constants in the argument, but nothing like 10 squared. But super cool. If you have a conjecture, you always want to know if it's at least good true in like the extremal case. So we have that at least. And then in 2015, Cranston Rayburn proved that delta is at least 13. They can almost get this big enough clique. They're about 3 vertices away. And then our result comes in, and we proved it for P5 gem-free graphs. So again, a P5 is a path on 5 vertices. Gem is a path on 4 vertices with a vertex adjacent to the whole 4 path. And so dash-free means, of course, we don't have these as induced subgraphs. And so our proof really stemmed from this global structure theorem. We sort of had 3 pillars. This is the first of the 3 pillars that held our proof up. And so Chernowsky, Karthik, Michelli, I'm afraid, proved in 2019 that P5 gem-free graphs satisfy Reed's conjecture. And in particular, they had this global structure theorem. They said if you're connected, P5 gem-free, and you have an induced C5, which we'll get, they got this through the strong perfect graph theorem. We did as well. Then you're one of 11 cases. You're the script H, or you're a P4 free expansion of G1 through G10. These are very small graphs at most 10 vertices. And so again, expansion means take each vertex, turn it into a P4 free graph, a graph with no induced P4. And then if there was an edge in the original GI, then you put a complete bipartite graph between the corresponding expanded vertices. And I'll show this visually in a little bit. But again, we have this awesome global structure. It gives us 1 of 11 cases to deal with. Then the next big pillar of our proof was the fact that Borden or Kostoshka proved in the 80s that if you're trying to prove for the Borden-Kostoshka conjecture for a graph family defined by forbidden-induced subgraphs, it suffices to assume delta equals 9. Basically, he did the inductive step. We just have to do the base case. And in fact, this is stronger. You don't have to do forbidden-induced subgraphs, any hereditary class of graphs. If you're trying to prove this conjecture for any hereditary class of graphs, you can assume the base case. So these are the 2 main pillars. This is sort of the big guns that held up our proof. We had sort of the smaller one, which is this local structure. Cranston and Rayburn proved in 2013 that if they proved a lot of stuff, but if you have any counterexample to the Borden-Kostoshka conjecture, they proved a lot of local things that can't happen. So these 2 subgraphs can't be induced anywhere in your counterexample to this conjecture. So whenever you try to prove this conjecture by minimal counterexample or by induction, you can assume these local structures don't show up anywhere. Another phrase is they're reducible configurations, although we don't use discharging, but you can sort of delete them in color and add them back in and extend the coloring. So those are the 3 main pillars: a global structure theorem, the fact that we can just do the base case, and some local structure. So this is how we set up the proof. Is let G be a P5 free, gem free counterexample that minimizes delta. So again, we can assume we're the base case, delta equals 9. Whenever you're trying to color, you always want to be vertex critical, and you can prove that here, even though we're doing induction over delta. It's just a sentence or 2 argument involving Brooks' theorem. And again, we get this induced C5 from the strong perfect graph theorem. If you're perfect, this conjecture is trivially true. So if you're not perfect, you must contain an odd hole or antihole of size 5 or greater. But if you're size 7 or greater, you either had an induced P5 or an induced gem, which we don't have. So your odd hole or antihole has to be size 5. And so that's how you get a C5, because both of those are equivalent. So sort of a tip of an iceberg thing. As soon as you look under the water, the strong perfect graph theorem is this huge gigantic thing. When I just say G has an induced C5, it's just the tip of the iceberg. That's a big result. So we get to use their global structure theorem. So we're 1 of 11 cases. So then here's the graphs. Like I said, relatively small graphs, G1 through G10. And in fact, we made the reduction down to a clique expansion similar to what they did in their paper. So basically for the P4 free expansion, you just take the P4 free parts and just trim down till you get to a clique, and you can show that your chromatic number, clique number, and delta stay the same. So it suffices just to assume you're the clique expansion. And the script H star is the clique expansion version of script H. Here it is pictured. The filled in vertices have to be cliques, but the unfilled vertex has to stay a P4 free graph. You can't get away with turning that one into a clique. And this fuzzy edge, this blob up here is a bunch of cliques, disconnected cliques. And the fudgy edge is just saying, like, for each vertex in the P4 free graph and the clique, there's either every edge or no edge. So it's sort of like a fuzzy half edge thing. Anyways, we're set up super nice. We're vertex critical, delta equals 9, and we're 11 discrete cases. It's what discrete math hopes for. And what's really great about these cases is when we first proved this, each case was like 2 pages. It was disgusting casework. It was awful. But through the amazing tool of greedy coloring, we were able to cut through those cases. Now each of them is about a paragraph. And all of them are independent and very similar. So I'm going to pick one and walk through it. It's a 1-slide proof. I definitely have enough time, 6 minutes, plenty of time. And greedy coloring, I think, is the thing to take away from this, especially degeneracy is what made this proof work. So assume we're a clique expansion of G3. So each xi is expanded to a clique qi. And if there's an edge in the original graph, you put a complete bipartite graph. Again, that's what these thick black lines are representing. Again, we can assume we're vertex critical and delta equals 9. And so we'll finish off this case in 4 claims. And again, every other case in this proof was played out almost exactly the same. So the first one is Q5 is strictly greater than Q6. It suffices to only prove that. If this is true, then my symmetry Q3 is strictly greater than Q7. The symmetry line, if you look at Q4, draw like a 45-degree angle going upwards. And that's the symmetry line. And then since each QI is non-empty, Q6 and Q7 have at least 1 vertex. So it would, in particular, this would prove that Q5 and Q3 have at least 2 vertices. So we just have to prove Q5 is strictly greater than Q6. We'll delete Q5. Here I have it grayed out. Color by criticality. Since delta was 9, we assumed this was a counterexample, so we need 9 colors to color it. But now that we've deleted some vertices, we can color with 8 colors. But if you look at Q5, its neighborhood is all of Q1 and Q4. But Q6 also has all of Q1 and Q4 in its neighborhood. So if Q6 is bigger than Q5, you can copy the colors from Q6 onto Q5 and get an 8 coloring of the whole graph, which contradicts that this was a counterexample. So Q5 is strictly greater than Q6, thus Q5 and Q3 have at least 2 vertices. And then here's the big claim. This is what made this whole proof sort of work, is this degeneracy argument. So Q4 is size 1. Let's assume otherwise. Let's say it has at least 2 vertices. Then we're going to get 2 independent sets, I1 in red, I2 in blue. We're going to delete them and show the resulting graph as phi degenerate. As a reminder, K degenerate means you have a vertex order where each vertex has at most K neighbors coming after it in the order. And so if you're K degenerate, this gives you a greedy coloring of K plus 1 colors. So if we show the resulting graph as phi degenerate, that means we can color with 6 colors, and then I1 gets the 7th color, I2 gets the 8th color, and that's a contradiction because we colored the whole graph with 8 colors when we assumed we needed 9 colors or more. And so we just have to show a vertex ordering where everything has at most 5 neighbors coming after it, after we delete I1 and I2. So Q4 prime here just means the vertices that are left in Q4 after deleting those 2 independent sets. So pick a vertex in Q4. What was its degree? Well, the maximum degree is 9, so it had at most 9 neighbors, but it lost 2 red neighbors and 2 blue neighbors. So it has degree at most 5. So it can trivially go in front of the vertex order. And then if you look at Q3 prime, which are the vertices left after deleting I1 and I2 in Q3, so say this black vertex in Q3, it lost a blue and a red neighbor, so it had degree 9, lost 2 neighbors, now it's degree 7, but Q4 had 2 vertices in it. So it has 2 neighbors behind it in the vertex order. So degree 7 minus 2 vertices behind it, and has at most 5 neighbors after it. And the argument continues and goes forward with these QI primes. It's the same thing, counting how many blue and red vertices did you lose as neighbors, plus how many vertices do you have behind you in the vertex order. Do you have 5 or less neighbors afterwards? You're good to go. So the resulting graph is phi degenerate, thus 8 colorable, which is a contradiction to this being a counterexample. So Q4 is just one big vertex. So that's the big thing, sort of, I don't know, as a grad student, when I saw greedy coloring and degeneracy, I thought, man, I'll only use this on homework. I'll never use it again. I was wrong. That's what grad school's for, to teach you that sometimes you're wrong. Greedy coloring, I should have never have discounted it. It is a great tool. And I hope you, maybe that's the big takeaway from this talk, is don't discount greedy coloring. It is very useful. The next claim is the degree of x2 minus x3 is at most 1, or this whole inequality. So the first part of it is pick a vertex x2 in Q2, pick a vertex x3 in Q3. Your degrees have to be 8 or 9, so the difference of them have to be at most 1. Why do they have to be degree 8 or 9? Well, if your degree is 7 or less, you can delete by criticality, color with 8 colors, add that vertex back in, and you have an 8th color available on that vertex. So the difference between any 2 vertices is at most 1 if you take the absolute value. But x2 sees q1 and q7 uniquely, and x3 sees q4 uniquely. So x2 will have the bigger degree. So you can get rid of the absolute value, and degree of x2 minus x3 is the most 1. The second part of the inequality comes from that same fact. If we're subtracting the degrees, you just have to count what does x2 see uniquely minus what does x3 see uniquely. So q1 plus q7 minus q4. Since q4 is size 1, you have this as at most size 1. So you sandwich the inequality, and implies that q1 and q7 have size 1. And then by symmetry, again, the symmetry line is q4 with like a 45-degree angle. You get the q1, q2, and q6 are size 1. And then we're done because q6 only has 1 vertex and it has degree 3, which is less than 8, strictly less than 8. So delete, color with 8 colors by criticality, add it back in, color the whole graph, which contradicts this was the counterexample. So again, all of our proofs played out almost exactly like this, 1 paragraph each. And the whole thing that held it together was this degeneracy. It really cut down the casework. So in summary, we're proving the Borden-Kostochka conjecture. We're doing this for P5 gem-free graphs, but you could sort of do the same structure with any hereditary class of graphs. You have to have a global structure theorem, which we got from Chernovsky et al. When they proved it for Reed's conjecture. Kostochka's base case lemma And we had some knowledge about some local structures. You didn't see it in this case, but we used it in the other cases. So thank you so much. Damn, I was 10 seconds over. I tried to get it on the dot.
It's okay. Thank you so much, Hudson, for the great talk. I'll take a moment to thank the speaker. Does anyone have any questions for Hudson?
I have a question.
You're right on the dot in my timer. Oh, go ahead.
Why did you choose P5 gem-free graphs?
Just from me and my advisor were looking for a project, and Chinosky et al. Posted their paper online on the archive, and we read through it, and just that global structure theorem was what sort of kicked us off. So I guess maybe that's not what you're asking. Are you asking why P5 gem-free maybe works for both papers?
Yeah, or just like why you explored it with that, and that was going to be a leading question for do you have any like next steps of types of graphs you want to try to prove this for?
So I tried to move on to some other project. In 2021, some people did prove using our paper the same structure for P5C4 free graphs. So you're totally right. This talk was sort of, I'm giving it here just because you could definitely imitate this. If you found the right things to forbid, P5C4 was the one people did this past year. I think it was Gupta and Pradhan, if I'm pronouncing those right. But the reason P5 and gem-free are picked is sort of, if you're P4 free, that implies you're perfect. You're a perfect graph, which trivially satisfies all these conjectures. So forbidding a P5 and something that's P4-ish, like a gem or a C4, sort of gets you like close to being P4 free. So that's sort of like the intuition. It's sort of like you're trying to forbid some graphs that basically makes you P4 free, sort of, which would give you the conjecture, I think, is the intuition behind picking these two specific graphs.
Gotcha. Thanks.
Yeah. So hopefully I answered your question. Sorry if I sort of rambled.
I have a question.
Mm-hmm.
Hey, Hudson.
Hey, Claire, what's going on?
So can you go back a few slides, like where you described the G1 through G10, like those
Right.
papers?
Yeah, sorry, lots of animations.
No, you're fine. Yeah, those.
Oh no, all right, there we go. Oh yeah, these right here.
Yeah, how are they characterized?
So the way they did this is their global structure theorem was basically their paper. Like their proof for Reed's conjecture was a paragraph, but the whole 8 pages was this global structure theorem.
Mm-hmm.
So the way they did it is when you have an induced C5, you can sort of beef this C5 up to be sort of like a clique or a P4 free expansion of a C5. And they slowly but surely just go out from the C5 and say, well, if you're adjacent to anything in the C5, you have to be adjacent a certain way. They had certain sets, they called them. And then there was a third layer where they're like, and then there's everything else. And then just case by case, they just showed if everything in the second layer is empty, this happens. Or if everything in the third layer and half of the second layer are non-empty, this happens. Like you get case G4. And then they're like, and so they just slowly, like you can see here in each of these cases, you can see the C5.
Right.
And then in G3, these two vertices right here were 2 parts of the second layer. And they're like, okay, what if the third layer and almost all the second layer were empty? Well, then you get G3. And and that's sort of what the proof did. And the other thing is they showed if there is an edge, then almost all edges are there. So they basically just showed it's super dense. And also the G1 through G10, like you're asking, came about when they just said, these 3 are empty, these are non-empty, you get G5. These 6 are empty, these 2 are non-empty, you get G7. Like that's how they went through it.
Okay, thank you.
Tedious casework.
All right, let's all take a moment to thank the speaker one more time for their great talk.